Hi, welcome to my basis behavior presentation. I'm Marcus Cox. The behavior I decided to go with for my presentation is called motion camouflage, which is a type of hunting behavior. The two taxa that this appears in is actually dragonflies, some of their relatives, and falcons. All right, so what is motion camouflage? Motion camouflage relies on a predator concealing its visible body movements by mimicking the optical flow of the background as seen by its prey, right? So this chart over here on the right shows just how they use this. So as an attacker, a falcon, we'll use a falcon for the example, right? So as a falcon approaches its prey using this behavior, it appears to remain stationary in the air. So according to the target, in this case, we'll say it's a crow, that falcon would appear stationary, not moving in the air until it's too late. So the falcon, in this case, this green line, and then the crow, the prey, the target will be this red line right here. As the falcon approaches its target, it keeps a set distance away, maintaining this optical illusion that it is stationary in the air until it gets close enough to actually strike and end that illusion. So classical pursuit will just the normal predatory bird that aren't falcons, they'll kind of just follow the prey. And once they get close enough, they'll kind of just follow behind it, giving away their position, not worried about stealth. And then this is obviously not as successful as motion camouflage, as they're able to get a lot closer and get their prey. This usually has a much higher success rate than classical pursuit. All right, so this video right here shows how that works. This red ball is a reference point. This yellow ball represents the falcon as it approaches the prey. And let me explain. The camera angle is also, it's going to be the prey, the view of the prey as it's being approached by the falcon. So the yellow ball, the falcon, this is a reference point to let you know how far away things are, and the camera is going to be the prey. All right, so you can see as the yellow ball approaches the yellow sphere, it appears to remain stationary because it's maintaining a certain set point as it travels until it gets close enough, and by then it's too late. You can see how quickly it got up close to the camera. That shows just how efficient this hunting can be. Skip genes in the environment. So we've talked about this. In order for animals to survive with these unique phenotypes and behaviors, they rely on their genes and environmental cues in order to attain them. Natural selection shows us certain phenotypes or certain looks are beneficial to survivability and fitness of an organism. We see this by the three types of selection that we went over in class. You have stabilizing, directional, and disruptive, each of these of which leads to a certain phenotype being preferred because it's better suited for that environment. We see this in peppered moths. So in an environment where the black phenotype is present, it's not as effective as camouflage as the white phenotype, right? So black is going to be outcompeted by the white. It's not as suited for the environment. And then, of course, the expression of genes passed down from parents to offspring. That's what's able to trigger certain proteins, which is able to produce these phenotypes. And genes can actually code for multiple different proteins, so it's sometimes not just phenotype that one gene is responsible for. This could be multiple different things. However, genes can also be affected by environmental cues, temperature, diet, change in their food, change in sun, moon cycles. All of that can have effects on their expression, and this can also occur during development. We see this in Himalayan rabbits who actually have a gene called the C gene, which is responsible for the development of fur pigmentation. So in higher temperatures, you'll see one type of fur pigmentation. I think it was white. And in lower temperatures, you'll get a different pigmentation. I believe in this case it was black. Phenotypic plasticity. So when an organism is in a unique environment, its behavior and phenotype can change as a result of being in that environment. And because this revolves around it actually being in that environment, mobile organisms that actually move from environment to environment may actually only receive these effects temporarily, as opposed to plants, which usually stay in one area. This is something that occurs more in plants. And because this change happens in one individual, you can see how one genotype can actually lead to multiple different phenotypes because it's one organism producing multiple different phenotypes. If one phenotype is able able to result in higher fitness, then we can see how phenotypic changes can have a big effect on evolution as well, right? Because higher fitness, to be able to produce more offspring, it's able to outcompete these other organisms. With all the goods that genes do, though, there can be constraints. An organism may react to an environmental cue at a wrong time or a bad moment, which could lead to a negative effect. In this example, we look at the red-eyed tree frog. The embryos of this animal actually uses light and night, day and night light signals in order to know when to hatch. But if the light cycle gets interrupted, or if there's danger present, like a predator, vibrations, it'll actually develop. It'll be born early, which could be fatal, right? Because it's not supposed to hatch early. You can see with these charts over here, no plasticity, and highly variable plasticity, right? You can see how certain traits are affected by that. Obviously, competition, non-competent changes. All right. The benefits of this behavior allows for animals to reach much closer proximity to their prey before actually engaging in that pursuit at the end, right? So the example we mentioned earlier with the falcon, it's able to get extremely close until that last moment where it's able to attack its prey. Optical illusions are actually something that's used quite often throughout nature. You can see in the background this cheetah. It's using you can see how even though the background, the vegetation isn't black, it's able to use these black spots to make it harder to see, which is the same reason why these black words right here are hard to see on this background, right? Even though it's not black vegetation, these black words are harder to see. An animal is able to maintain its speed while at the same time being stealthy, which is a huge advantage of this. It's able to maintain mobility and stealth, which gives it the high success rate that it gets for catching its prey. In this video right here, you can see how this actually isn't an example of the camouflage that we're talking about. This is an example of camouflage that's facilitated by motion, right? This isn't motion camouflage. It's using the phenotype of this animal and using motion to kind of use it as camouflage. So you can see a little bit further on how even as it's approaching this animal, I believe, which is colorblind, making it even harder to see, almost looking directly in that direction, it's still able to move, maintaining this optical illusion, right? To get extremely close distance. Now, this isn't motion camouflage, but it's a similar kind of principle, right? All right. I wasn't actually able to find a video of a dragonfly exhibiting this behavior, but I wanted to point out a few similarities between the falcon and the dragonfly that make this happen, right? So, first of all, the eyes on this dragonfly, it's almost all eye on the head, right? Extremely good eyesight, so it's able to see its prey and form that motion, that behavior as it attacks. And also, the 4 wings on this dragonfly have separate muscles for each of them. It gives it extremely good mobility in the air. Falcons also have both of these, extremely good eyesight and extremely good maneuverability in the air. So you can kind of see why they would both use this behavior. Sorry about that. All right, so what are the costs of this behavior? It relies on the attacker to keep a certain position, maintain that optical illusion up until it strikes its prey. Otherwise, it'll lose it, it'll be spotted, and it won't get it. Unlike other forms of camouflage, this attacker, it has to remain mobile. It doesn't remain stationary, much like this caterpillar in the back. It has to actually go get its prey as opposed to being an ambush predator or something where it would wait for its prey to come. Meaning that the attacker has to be healthy. It has to be both stealthy and efficient, right? It can't just be efficient because it won't be able to have that stealth to get closer. It can't just be stealthy because it won't have the efficiency to finish the pursuit. How did this behavior come to be? Simple competition, like you'd say competition, right? It's able to outcompete all of these other animals. You can actually see that right here. This example, we see a peregrine falcon as it pursues a large group. And both dragonflies and falcons are able to do this. They're able to pinpoint one animal out of a group. In this case, you can see it's going to be this bird right here that it decides to pursue. Right here, it follows it, maintaining that set distance right up until striking its prey, and it starts the pursuit here, but right when it's close enough, giving it better chances at catching. Then it catches its prey. All right, so that was my example, and that was my presentation. Thank you so much for watching.